Stop sharing and figure out where I'm at now. So I'm in this Clojure book called the Clojure Workshop. It looks like I'm at this section right here, the meditate function version 2.0. Maybe? No, I did this already. Let me launch my IntelliJ. Yeah, I did this already. The meditate function. Okay. Meditate. I did this. Meditate. What we know now. This looks unfamiliar right here. Close. All this. Define function, change color. Color takes. All right, so like it's this stuff right here. It would check that the columnist level is exactly 10 and return the reverse of the string when that is the case. It looks like I did a previous version of this. Yeah, I'm not doing that. Where's it go? Oh shoot, that's in the chapter. Hold up. In this chapter, we discover how to use the REPL and its helpers. You are now able to search and discover new functions and look up their documentation interactively in the REPL. We learn how Clojure code is evaluated, as well as how to use and create functions, bindings, conditionals, and comparisons. These allow you to create simple programs and scripts. In the next chapter, you look at data types, including collections and the concept of immutability. All right, good stuff. I graduated to the next chapter. Data types and immutability overview. In this chapter, we start by discovering the concept of immutability and its relevance in modern programs. We then examine simple data types such as strings, numbers, and booleans, highlighting subtle differences in different environments like Clojure and ClojureScript. After a first exercise, we move on to more elaborated data types with collections such as lists, vectors, maps, and sets. Learning along the way which to use in a different situation. After touching on the collection and sequence abstractions, we learn new techniques for working with nested data structures before finally moving on to the final activity, implementing our very own in-memory database. Okay. Now, like I'm doing this in preparation for my session with Sergey, which has been pretty proactive in our weekly Clojure sessions as he mentors me. And so I just want to be prepared, a little bit more prepared, so that I'm just not wasting this time. So that's why I'm going through like these exercises or these chapters, so that when we do talk, at least it shows that I'm trying, even though I honestly don't have the time. Speaking of which, do I need to check my thing? Yeah, no viewers. Okay. By the end of the chapter, you'll be able to work with a commonly used data type structure. Commonly used data types in Clojure. It's weird how my brain will like completely say something that's not being read. Introduction. Computer hardware has evolved dramatically in the last few decades. On a typical computer, storage and memory capacity have both increased a millionfold compared to the early 1980s. Nonetheless, standard industry practices in software development and mainstream ways of programming are not that different. Programming languages such as C++, Java, Python, and Ruby still typically encourage you to change things in place and to use variables and mutate the state of a program. That is, to do things as if we were programming on a computer with a minimal amount of memory. However, in our quest for efficiency, better languages, and better tools, we reach for higher level languages. We want to get further away from machine code. We want to write less code and let the computers do the tedious work. We don't want to think about the computer's memory anymore, such as where a piece of information is stored and whether it's safe and shareable. As much as we don't want to know about the order of the instructions in the CPU, it is a distraction to the problems we are trying to solve, which are already complicated enough. If you have ever tried to do some multi-threading in languages cited previously, you will know the pain of sharing data between threads. Although leveraging multi-core CPUs with multi-threaded applications is an essential part of optimizing a modern program's performance. In Clojure, we work almost exclusively with immutable data types. They are safe to share, easy to fabricate, and improve the readability of our source code. Clojure provides the necessary tools to write programs with the functional programming paradigm. First-class citizen functions, which we will discover in the next chapter, and avoiding mutating and sharing the state of an application with immutable data types. Let's dust off the dictionary and look up the definition of immutable. Immutable, that cannot be changed, that will never change. It doesn't mean that a piece of information cannot change over time, but we record those modifications as a series of new values. Updating an immutable data structure provides a new value derived from the original value. However, the original value remains unchanged. Those data structures that preserve previous versions of themselves are called persistent data structures. Intuitively, we may think that such a persistent data structure would negatively impact performance, but it's not bad as it seems. They are optimized for performance, and techniques such as structural sharing bring the time complexity of all operations close to classic. Immutable implementations. I don't really know what it means. In other terms, unless you are programming in an application that requires extraordinarily high performance, such as video game, the benefits of using immutable data structures far outweigh the small loss in performance. So then the next section is simple data types. All right. A data type designates what kind of value a piece of data holds. It is a fundamental way of classifying data. Different data types allow, or yeah, I did it again. Different types allow different kinds of operations. We can concatenate strings, multiply numbers, and perform logic algebra operations with booleans. Because Clojure has a strong emphasis on practicality, we don't explicitly assign types to values in Clojure, but those values still have a type. Clojure is a hosted language and has three notable major implementations in Java, JavaScript, and .NET. I don't think there's a Clojure for .NET. Hold up. I don't, I don't believe that. Mm, I don't believe that at all. 5 months ago. Let's see what they have in here. Yeah, it's 5 months ago. Go back over here. Clojure CLR is the name of it. This project is a native implementation of Clojure on the Common Language Runtime. The execution engine on Clojure is programmed in C# in Clojure itself. Implement a feature complete Clojure on top of CLR. Stay as close as possible to the JVM implementation. Have some fun. What's this over here? Nothing. All right, go back. Clojure is a hosted. I did that part. So, being a hosted language is a useful trait that allows Clojure programs to run in different environments and take advantage of the ecosystem of its host. Regarding data types, it means that each implementation has different underlying data types. But don't worry, as those are just implementation details. As a Clojure programmer, it does not make much difference. And if you know how to do something in Clojure, you likely know how to do it in, say, Clojure script. In this topic, we will go through Clojure's simple data types. Here's the list of the data types looked at in this section. Please note that the following types are all immutable: strings, numbers, booleans, keywords, and nil. Strings are sequences of characters representing text. We have been using and manipulating strings since the first exercise of Chapter 1. Hello, REPL. You can create a string by simply wrapping characters with double quotes. I am a string returns I am a string. I am mutable returns I am mutable. String literals are only created with double quotes, and if you need to use double quotes in a string, you can escape them in the backslash character. That guy runs like me. What did it say? String literals are only created with double quotes. If you need to use double quotes in a string, you can escape them with the backslash. Okay, I got that. So they have an example of embedding double quotes within the string, in which they have backslash and then the measure of the intelligence of the ability to change, and then backslash again. Albert Einstein. All right, got that. Strings are not able to be changed. They're immutable. Any function that claims to transform a string yields a new value. Got it. Okay. In the preceding example, calling Clojure.string.replace on silly string, return a new string with the word silly replaced with clever. So I think they're talking about this right here. Clojure.string.replace, and then they provide silly string, in which they're looking for occurrences of silly with clever. Okay. However, when evaluating silly string again, we can see that the value has not changed. The function returned a different value and did not change the original string. Got it. Although a string is usually a single unit of data representing text, strings are also collections of characters. In the JVM implementation of Clojure, strings are of the java.lang.string Java type, and they are implemented as collections of the java.lang character Java type, such as the following command, which returns a character. So they have first a collection of characters, and that's going to return A. And I guess it returns the backslash A to represent a quote. First turns the first element of a collection. Here, the literal notation of a character is, oh shoot, what just happened? Here, the literal notation of a character is backslash A. The type function returns a string representation of the data type for a given value. Remember that. All right. Remember that we can use asterisk 1 to retrieve the last return value in the REPL. So asterisk 1 evaluates to backslash A. It is interesting to note that in Clojure script, strings are collections of one character strings because there is no character type in JavaScript. Here is a similar example in Clojure script REPL. Last is the function, and the parameter that we're providing is a collection of one character strings, and it's going to return S. Okay. As with the Clojure REPL, type returns a string representation of the data type. This time, Clojure script, the value returned by last function returns the last character of a string. It's one of object string type, which means a JavaScript string. Okay. So in the example, they have within parentheses type, and then the last argument that's denoted by *1, and it returns a pound object, and then within brackets string. You can find a few common functions for manipulating strings in the core namespace, such as stir, which we use in chapter 1, to concatenate, combine multiple strings together into one string. So string, that's the way you, and then concatenate. Crap, what just happened? What just happened? I accidentally went to another page. That's where you concatenate. All right, that's most functions for manipulating strings can be found in Clojure.string namespace. Here's a list of them using REPL, dir function. So within parentheses, dir Clojure.string, and then blank capitalized ends with escape, and then it's probably going to keep on going. Includes index of join. Okay. So it looks like you can use the dir function plus a namespace to get all the functions that are in it. Got it. Hold on, where's concat at? I thought concat was part of Clojure.string. Where's concat? That's not. So that's the Clojure.string namespace. Where did concat come from? It's just str, which is, I guess, part of Clojure.core. Nah, man, F that. Hold up. Clojure. Stir. Yeah, it's in Clojure.core. Oh, how come stir isn't part of the Clojure.string namespace? Remove that. I don't understand that. Whatever. So there's a Clojure.core that has a string function, and then there's Clojure.string. Yeah, I'm not gonna understand that. As a reminder, this is how you can use a function from a specific namespace. Clojure.string / includes with a question mark, and then you have potatoes, toes, and it's going to say true. Potatoes includes toes. So why is there a question mark at the end of it? Is it because it's a Boolean function? That's why we use a question mark. We will not cover all the string functions, but feel free to try them out now. You can always look up documentation of a string function from the preceding list with the doc function. Yeah, it looks like all their predicates have a question mark on it. Does that mean that I could just define a function with a question mark? So like if I do change color, I'll put a question mark on there. I do shift alt load. Hold up. How do I do this? Oh, shift alt. I gotta run my REPL. Hold up. Run the REPL. All right, and then I do a shift alt L, and it's gonna say that change color. I'm referencing change color somewhere. Okay. So I'll put it right there. Shift Alt L. Okay, so you can have question marks. So what can I put a question mark instead of a dash? Well, let me do that too. Shift Alt L. Yep. Okay, got it. That's interesting. Periodically check. All right. So you can have question marks in your value or function declarations, or you can have question marks. You can have the question mark character in your declaration. All right, so we will not cover all the string functions, but feel free to try them out now. You can always look up the documentation of a string function from the preceding list with the doc function. So then we have numbers. Clojure has a good support, or Clojure has good support for numbers, and you will most likely not have to worry about the identifying type or underlying types, as Clojure will handle pretty much anything. However, it's important to note that there are a few differences between Clojure and Clojure script in that regard. In Clojure, by default, natural numbers are implemented as the java.lang.long Java type, unless the number is too big for long. In that case, it's typed as Clojure.lang.bigint. So, like, type 1 is going to return, or within parentheses, type 1, because type is a function, and then you pass whatever value, and it's going to return to java.lang.long. If within parentheses you say type dot 1 trillion, I think that's bigger than trillion, 1 gazillion is going to return that's going to return a java.lang.long. And if you have more zeros to it, it's going to return the Clojure.lang.bigint. So if you notice, it still relies on the Java libraries, but then it still relies on the data structures within the Java SDK. I'm not even saying that right. Software development kit. It's not SDK. It still relies on the libraries or the Java compiler, but then like for really big numbers, it's going to be defined in Clojure. Well, why didn't I mean you could represent a big number? I'm sure in Java. Why didn't it do it in Clojure, or why did it do it in Clojure? So then they say, notice in the preceding example that the number was too big to fit in the java.lang.long Java type, and therefore was implicitly typed Clojure.lang.bigint. Exact ratios are represented by Clojure as ratio types, which have a literal representation of like 5/4. It's not an exact ratio, so the output is the ratio itself. So 5/4 is going to return 5/4. The result of dividing 3 by 4 can be represented by the ratio 3/4. So you say 3/4 is how you represent it, and it's going to return you 3/4. But you're doing division because you're saying like 3 divided by 4. But if you have like, I don't know what you call it, when you have, what do you call that thing? Is that really called a ratio? I mean, they call it a ratio when the first number is larger than in the fraction. In the fraction, the numerator is larger than the denominator. Is that what the ratio is? I don't think so. Whatever. So yeah, whenever you want to do a normal fraction where the numerator is less than the denominator, then you have to have the divide operator as the first argument because you're but it's not really performing a calculation. It's just It's just representing that expression in a different way. Yeah, so like I would expect this to be a decimal. Hold up, we gotta see this. Well, how do you cast it to a decimal? I mean, how do you not a decimal, a float? Like, how would you cast that to a float then? So like apparently this data type is called ratio, and that's a default return type of this. How do you cast it to a bool? I wonder if they're gonna say that 4 divided by 4, it's not less than, so it's gonna return 1. Decimal numbers are double precision floating point numbers. Okay. What else? If we take our division of 3 by 4 again, but this time mix in a double type, we will not get a ratio as a result. So 3 divided by 4.0. Oh, okay, that's how you get it. This is because floating point numbers are contagious in Clojure. Any operation involving floating point numbers will result in a floating or a double. Will result in a float or double. So 1.0 times 2 is going to be 2.0. And we see that the return type of that is double if we call the type function and pass in that expression. Let's go ahead and try that. Within here, we can say type. And then within here, we can say 1.0. But we can say 1.0 times 2. So load that whole thing, Shift Alt P. Okay, and that's going to be a double. In ClojureScript, however, numbers are just JavaScript numbers, which are all double precision floating point numbers. JavaScript does not define different types of numbers like Java and some other programming languages do. For example, long, integer, and short. 1, 1.2, 0.75, 0.75, 2. Notice that this time any operation returns a floating point number. The fact that there is no decimal separation for 1 or 2 is just a formatting convenience. We can make sure that all those numbers are JavaScript numbers. Yeah. No, hold up. We did. No, that's not right. We did. Okay, so if they want to force 3/4, then they do that right there. Okay, I got it. Hold up. So, like, if they just do 3/4, that's kind of like the literal. I'm confused. Hold up. How did they do it last time? They had 5/4. All right, let's try 5/4. Oh, they didn't have it wrapped in parentheses. So if you don't wrap it in parentheses, hold up. Oh, crap. You just have 3/4. It doesn't evaluate it at all. All right, man. Whatever. Type 1 is a number. Type 1.2 is a number. All right, so what's a number? Hold up. Why didn't it? They're talking about the differences between ClojureScript and Clojure. So they say in ClojureScript, however, numbers are just JavaScript numbers, which are all double precision floating point numbers. JavaScript does not define different types of numbers like Java and some other program languages do, for example, long integer and short. Notice that this time, any operation returns a floating point number. The fact that there is no decimal separation for 1 or 2 is just a formatting convenience. All right, well, I don't care about ClojureScript. If you need to do more than simple arithmetic, you can use the Java or JavaScript math libraries, which are similar except for a few minor exceptions. The Obfuscation Machine. You have been contacted by a secret government agency to develop an algorithm that encodes text into a secret string that only the owner of the algorithm can decode. Apparently, they don't trust other security mechanisms such as SSL and will only communicate sensitive information with their own proprietary technology. You need to develop an encode function and a decode function. The encode function should replace letters with numbers that are not easily guessable. For that purpose, each letter will take the character's number value in the ASCII table, add another number to it, the number of words in the sentence to encode, and finally compute the square value of that number. The decode function should allow the user to revert to the original string. Someone highly ranked in the agency came up with that algorithm so they trust it to be very secure. In this exercise, we will put into practice some of the things we've learned about strings and numbers by building an obfuscation machine. Start your REPL and look up the documentation of the clojure.string.replace function. Okay? In parentheses, clojure.string/replace. We're supposed to say like doc, right? No, you're supposed to say doc before. Oh, okay. Like that. Push FP. This is the documentation, which somehow doesn't. Okay. Okay. Notice that the replace function can take a pattern and a function of the matching result as parameters. We don't know how to iterate over collections yet, but using the replace function with a pattern and a replacement function should do the job. So in the documentation, they provide an example, I think. Clojure.string/replace, almost pig Latin. Then they have like this, it looks like a regular expression maybe. And then almost igpe atinle. Okay. Notice that the replace function can take a pattern, blah, blah, blah. We don't know how to iterate over collections yet, but use the replace function with a pattern, and a replace function should do the job. Try and use replace function with the pound within double quotes \w pattern, which means word character. Okay. Replace it with the exclamation character and observe the result. Okay. So they're saying in parentheses clojure.string forward slash replace, and then they're going to have a hello world as the first argument. And then they're going to say take pound within double quotes, take pound within double quotes, and backslash W to denote a word, and replace it with an exclamation point. Is that pound sign like a macro or something? Control Shift P. Yeah. All right, so try and use the replace function with the same pattern, but this time pass an anonymous function that takes the matching letter as a parameter. So we do the same thing, except the argument is going to be a function that takes a letter and then is going to return a side effect of print line letter. All right, I can try that. I'll copy this. I'll go to the next line. And here, I think they're saying it's going to, don't I have to do this like within parentheses? Oh. All right, let's just do that. And then I think they're saying you declare a function that takes, was it a letter? How did they say it? Yeah. And then while still within those parentheses, we say do, and then print line or print. I'll just say print. And then within here, do the double quotes. That looks fine to me. Is that how they had it? They did print line letter, and then they had double quote. This is confusing. They had print line letter, and then how do they do this? Then they had an exclamation point. So let me read this. There's a replace hello world that for each word is what we want to search for. We're going to take a function that takes a letter and it's going to return. I don't know what this doesn't make sense to me. Maybe because the last line is what gets returned. Okay, I get that part. So you can execute whatever you want to execute. But at the end of the day, it's the last statement that gets returned. Okay, I got that. Observe that the function was called for each letter, printing the match out console, and finally returning the string with matches replaced by the bang character. It looks like we should be able to write our encoding logic in the replacement function. Now let's see how we can convert a character to a number. We can use the int function, which coerces its parameter to an integer. It can be used like this. Really? Int a? Int backslash a. Why does it always have to have? Why do we have to have a backslash? Is that just for a single character? You always have to have a backslash? Like, what if you just wanted to have? Did you do this? So it looks like whenever you want to refer to an individual character, you have to have a backslash. It means the characters following should be interpreted as a literal. When you see a slash before a single character, it means it's not a string but a Java char instance. Okay. Speaking of which, what do I get a point for? All right, so there's a function that will translate. Let me clean this up. There's a function that will translate a to. Oh, what is 97? Is that the ASCII number? We can use the int function, which coerces this parameter to an integer. It can be used like this. Since that the replacement function will take a string as. How is A 97? Hold up. ASCII code is 97. Okay. And how do you know the ASCII code is ASCII deterministic? If you use the full range of 0 to 15, if you want to parse a 2 to 3 digit decimal value, ASCII values, you can make the part if you limit the range if possible. Okay. Now let's see how we can convert a character to a number. We did that. Seems like that replacement function will take a string as a parameter, so let's convert our string to a character. Use the character array function combined with the first two, with first to convert our string to a. Now, if we combine previous steps together and can also compute the square value of the character's number, we should be approaching our obfuscation goal. Combine the code written previously to obtain the character code from a string. Okay. I'm starting to get tired now, so I'm going to tap out. But I think I don't know. There was a little bit more clarity. I'm out. See ya. Bye.